אני זוכרת שממש לקח להם זמן עד שחשבו לי לחשוב על דיבחן, היה לי הקורונה.
הזמן של ה...
הסר הזה, היה ממש סוגיה אז שנה
אני חושבת, בחיים לא הייתי יודעת. למה שם שהיא מתחילה להתקבל?
לא, עכשיו אני מרגיש שזה הוא היה גאוני, עכשיו זהו כתוב לו, עכשיו לא ידע את זה, זה חלק מההיסטוריה.
מה נשמע? נכנסתי ברגל ימין, אמרתי יאללה, רק
מקווה שלא תצאי ברגל שמאל.
לא, לא. כולנו זוכרים מה שעשינו למראה. אנחנו נבוא
Hi everybody, we are starting. So this class is going to be in English. Well, you'll get a chance to practice your English. If you're really not fluent in English, you can ask me in Hebrew and I will translate for everybody. I will also slow down a little bit due to this language barrier. Alright, so my name, whoever does not know it yet, so my name is Stas Burov. Okay, email stasbur@gmail.com. Please don't send me any messages via not in bar. What's the other system? Moodle. I don't see them. Just write something, anything that you want. Write to my email. I usually respond pretty fast. I sit in room or building 202, room 314, the pie room. Okay. What else you need to know? So this is a continuation, or supposed to be a continuation of thermodynamics. But if you've forgotten what you got in thermodynamics or you didn't like thermodynamics, don't worry. I will try to remind you, at least at the first part of this class. We have 3 lectures per week. We have 1 TA session. The grades, which is probably the most important for you, are chosen in the following fashion. So 11% is homework, 22% are quizzes. We are going to have 2 during the semester, and we usually take the best outcome out of the 2, and 67% is the final exam. Now, you do have to submit the homework. It's not that everybody gets 100 points for homework, but you have to submit the solutions. Why I'm telling you this? Because it's a common situation that students submit blank pages, poems, doodles, cartoons, whatever. Okay, so this is not going to be graded. We do check if you are submitting solutions, right? We don't really care if the solution is correct, but the TA assistants will go through your submitted homework and check if you actually did some work. Now, it's really, really important, at least in this class, that you do all the homework or try to do all the homework on your own during the semester. It's almost impossible in this class to get a passing grade. I'm not talking about good grade, passing grade, okay? If you do not work during the semester. So I'm trying to scare you a little bit, but this is the actual situation. So last year, 23% failed after 3 trials, not 2, 3. Great, right? Okay, so, but this is actually happens mostly to people who decide that it's going to be okay to study everything by the end of the semester. And this kind of material that we're going to learn in this class is something that has to penetrate slowly. Okay? This is a lot of statistical thinking, which usually we do not accustom to. So it's a process. And if you think that you can start this process 7 days before the exam, well, usually it will fail you. We are very flexible, so if you have any requests, if you cannot submit your homework on time, or you're not going to make the quiz, etc., please write me or to the TAs an email beforehand. Okay, so we cannot address any requests that will come at the end of the semester saying, well, I couldn't come to the quiz. Okay, do it before the quiz, do it before the homework has to be submitted. Any questions? Are you fine without the lights over there?
It's flashing. It's better.
Flashing. Okay. Okay. Any questions about the technical part of the class?
You already know when the quizzes are going to be?
So yeah, I will publish this later today. I don't remember the exact week, but I think the first is like 4 weeks from now, and the second. So one at the end of the November, the other one is by the end of December, approximately.
יש נבחנים ולוקחים את הטוב מביניהם, נכון?
Yeah. So the question is, there are 2 quizzes, and I take the better grade. Yes.
And I also have a question.
Yes.
Do we have to take both of the quizzes if we have?
It's your choice. I don't care. So the question is, are the TAs teaching in Hebrew or in English? So there is one class, שיעור אחד באנגלית, and 2 classes in Hebrew.
Which of them?
I don't know. So yeah. So in bar you can check. It's actually written there.
The tests and the homework are in Hebrew or in English?
Good question. So the test usually comes. The test, I can assure you that the test and the quizzes are going to be in both languages, right? The homework, I haven't thought about it. Okay, so, but I think it's a little bit less critical because.
Yeah.
Any other questions? שאלות נוספות? לא. Okay, so what is statistical mechanics is about?
It's the
Oh yeah. So all the bibliography is actually written in the Moodle page, but the books that I use most is Introduction to Modern Statistical Mechanics. Statistical Mechanics by Chandler. The other one is Statistical Thermodynamics, I think it's called. Statistical Thermodynamics by Callan. I think it's H. Callan. I don't remember his first name. Alan. Another book which is good, but it's a little bit outdated. It's Statistical Physics. By Landau and Lifshitz. Now, the thing is I'm not following any one of those books. So part of the subjects are going to be taken or nicely presented in this book, part of them nicely presented here, and part of them nicely presented here. So it's just like some sort of a jump between different books. If you wish to really know where I'm taking this material and where I think it's presented the best to follow the class, please write me an email and I will tell you. Okay? Yes. Another question. In the exam, no. So the exam is a regular exam. You can, I will provide you formulas in advance before the exam. You will know what you have, what formulas are going to be provided, and that's it. Okay. Yes.
You wrote London and something. What is it?
Lifshitz.
Lifshitz.
And Lifshitz. Landau and Lifshitz. So it's a very popular series, Landau and Lifshitz. He was a very great scientist. He was a very good book writer. Okay. Anything else? Okay. Statistical mechanics. So what it is about? If you remember from thermodynamics, it depends where you have been studying it, but usually thermodynamics starts with a lot of strange postulates and axioms about how heat flows from one place to another. Our class will start with this too, but the goal is a little bit different. The goal of statistical mechanics is to explain how systems are operated when the systems are complex. When they are complex and then they have inside of them many ingredients. Okay? Why it's so important? Well, if we look around us, we would see that nothing is actually a point particle of mass m. Right? So when you started to learn physics, undergrad studies, mechanics or physics 1, it's all started with, I have a point particle of mass m, I can write my Newton equation, right? Something like that, and solve everything. I can exert forces on the particle, can exert some sort of constraints, but everything is solvable. Right? We can complicate this a little bit more. We can say, well, we don't like the Newtonian formalism. We like the Lagrangian formalism. Or we have the Hamilton formalism. It's still solvable, completely solvable. Even if I will tell you, well, this is a quantum particle, right? And I would write an equation, for example, the Schrödinger stationary equation, I still can solve it. Right? So the potential can be a little bit complicated, but generally there are methods to solve everything that is connected to one single particle of mass m. All right. Now, if I add another particle, okay, so this is going to be m, this m1 and m2. Okay. I have two particles. These two particles I can still deal with, right? So I usually can transform any problem where there are interactions between m1 and m2 to two separate problems where each of them is describing one particle and another one is describing another particle, non-interactive. Okay, so one body I can solve, two body I can solve. I'm proceeding in the same fashion and I add a third particle, right? And 3. So the transition from a situation when I have only m1 to the situation when I have m1 and m2, it's pretty easy, right? I can transform it to the center of mass coordinates and work my way around. But when I'm going from m1 and m2 to the third particle, this is what is called three-body problem. I'm stuck. Okay, so it's an extremely small change from 2-body to 3-body, but this problem is already unsolvable. Right? What do you mean unsolvable? This problem was known from the mid of Newton already, and people are trying to solve it for the last 300 years, and in most cases, we do not know how to solve it. Moreover, we do know that this system sometimes can be extremely sensitive to initial conditions or to the specific starting conditions of my problem. So there is an emergent chaotic behavior only from 3-body problem. There are papers even now, right, if you want to write a very good paper that will be published in such journals as Nature, etc. So this is still a simple but a very important problem. So if you make an advance on this problem, it's a publishable material, not just in some paper who nobody reads, but in very, very good journals. Right? So we're stuck, and you see around us that we don't have problems which are involved 3 bodies. Maybe in celestial dynamics, right? We have sun, we have moon, and we have Earth, and we cannot really solve it. Right? We can maybe simulate it on a computer. Approximation. But even this, okay, so this is for any situation when you have pairwise interactions. For example, if I have 3 particles and I will immerse them in water, okay, the simulation of this system is already something very complicated and very untrivial. The moment I have even non-pairwise interactions, or what is called hydrodynamic interactions, it's extremely difficult not to solve analytically to obtain some formula, but even to simulate it on a computer approximately, it's pretty hard. So what I'm trying to claim over here is that whatever you have studied is usually not applicable to the real world, right? Because if you look on every system, like this notebook, there is a lot of particles, a lot of different atoms, a lot of different molecules, a lot of different pages, right? How can I describe the dynamics or the nature of my notebook when I'm already stuck with 3 particles? So statistical mechanics, which is originated from thermodynamics, is trying to answer to this question, to find an answer to this question. And it's amazing that we do not know how to solve problems that involve 3 particles. We don't know how to solve problems that involve 4, 5, 10, but we do know how to solve problems that involve 10 to the 10 particles. Okay? So there is a huge gap between this system and a system that involves huge a number of molecules, and we know that somewhere in between we lose our knowledge completely of how to treat the system, but we do know that there are new and emergent laws that appear only on the scale, large scales. Okay? So we need a lot of different particles, and somehow those very specific interactions that occur between the different ingredients become unimportant. Okay? Completely unimportant. Moreover, the laws are very unspecific and very universal. So universal laws for many particles. It appears that if I want to describe a traffic jam, or I want to describe colloidal particles, or I want to describe virus inside a cell, by a cell, okay, the description by the laws of statistical mechanics is going to be the same. And the behavior for all those 3 completely different questions, right? Traffic jam, motion of people, colloidal particles that are some small plastic particles of 10 to the minus 3 meters radius, or if we're going even smaller to the virus inside the biological functioning cell, somehow, because all the environment involves many different particles, all those three systems, and many, many, many more that we would think that they are completely different, they still have the same laws that direct the motion of single cars or particles or the viruses. Now, this is something which is a little bit amazing, or truly amazing, right? You have one very specific behavior on the microscale, where all the different specific laws and interactions are important and everything is very, very complicated. But when you go to much larger scale, new laws appear, and somehow those new laws are non-specific, much, much, much more easier than the regular laws of Newton or, or the quantum mechanics laws, but they make us think in a different fashion. They make us think probabilistically and statistically, right? And this is something that we are going to learn during this class. Now, in Israel, we really love to perform statistical experiments. We have elections next week, right? So I hope that you will enjoy this class. All right, so we are not going to treat traffic jams right now, or biological cells, or artificial intelligence. That, by the way, right, all the different AI's algorithm that you now see everywhere, right? You open YouTube and you have a specific song that is playing, chosen by you by some algorithm. All the basis of those AI algorithms is actually coming from statistical mechanics. They're called Boltzmann machine, and Boltzmann is one of the grandfathers of this field. Again, you have huge number of ingredients, and somehow out of those ingredients, very nice and specific behavior occurs. Now, before we're going to learn about traffic jams, AI, we're not going to learn about AI, but a little bit more advanced. I would like to remind you what you should know from the class of thermodynamics. Okay. So, thermodynamics, we start with the first law of thermodynamics, which is conservation of energy. Any questions? Okay, so what do we know? We know that in any closed system, the energy is conserved. Now, I'm not getting into the discussion what is energy, because we don't really know what is energy. We know that there are specific mathematical forms that are conserved. We know what is a kinetic energy, we know what is a magnetic energy, we know what is a potential energy, we even know what is a heat. Okay? And we know that if we sum all of those guys together, a constant value appears no matter what we do to the system. Again, in thermodynamics, as long as we keep this system closed. Okay. So if we have a system, and we call the energy of the system is E, right? So no matter, as long as we are not introducing new particles or there is no heat flow inside the system, this energy is going to be constant no matter what is happening inside the system. Okay. All right. Now, the energy, again, in this thermodynamical world, is assumed as an extensive quantity. What is an extensive quantity? Let's assume that we have, instead, one system, we have two systems, A and B, and we have the energy of system A, E1. The energy of system B is E2. Now, I would like to ask you, what is the energy of the system A plus B? Okay, so what do you expect the energy of A plus B to be? E1 plus E2. Okay, but I'm playing the devil's advocate over here. What about the interaction energy? What about this? I had two magnets, right? I connected them, and I'm saying, oh, this is the energy of this guy plus the energy of second guy, and now I'm connected them, and the energy is still the same. Maybe some energy is gone into the connection between those two guys, right? Yes or no?
Well, then it's no longer a closed system.
Why? I had E1, I have E2, I somehow now connected them. What is the energy of the system? This is called an interaction energy. Interaction energy. Okay. Right. I have M1 and I brought M2. Okay. The energy is the energy of M1, the energy of M2, and some interaction energy between M1 and M2. Right? For two particles. Why here, and this is one again the part of the postulates of thermodynamics that we are going to use for the whole semester, E of A plus B, as you said correctly, is indeed E1 plus E2. Okay. Why can say that? Because in all our system or our discussions, we're going to neglect this interaction energy. The answer is that if this system is huge, and this system is huge, indeed, there is some sort of interaction between those systems. But this interaction is limited only to the boundary. And the whole system is much, 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 much larger than the boundary. Okay? Therefore, I can neglect the interaction energy. Okay? So it's not exactly an equality here. It's approximately equal. But for our purposes, we're going to use it as exactly equal. Now, there are systems that do not obey to this law. For example, systems where the interaction is extremely long, right? Magnetic system, for example. The magnetic interaction are spreads not just on the small boundary, but it spreads for all over the system. So I cannot neglect it, right? We are treating system where this interaction energy can be completely neglected. Okay? So this property that I have two systems, E1 and E2, and I'm neglecting the interaction energy, I'm calling that this is extensivity of the energy. In Hebrew, godel extensivity. Okay? Extensivity, godel extensivity, the same. I'm E. Any system, E is an extensive quantity, and it is a quantity that can be composed on two other subdivisions. כל גודל שהוא חיבור של שני גדרים אחרים, גודל אקסטנסיבי. Yes.
הבנתי, אבל כאילו, יש לך שתי מערכות, שלאחד יש כאילו נגי אחד ואחד נגי שתיים. עכשיו, אם כאילו יש איזושהי אינטראקציה, אז כאילו, אנרגיה יכולה לעבור בין אחת לשנייה, אז מה הכוונה באנרגיה באמצע?
Very good question. So, the question was, well, I have E1, I have E2, I somehow connected them. Well, there could be flow of energy between those two guys, right? I don't care. The energy hasn't disappeared, right? The energy hasn't disappeared. The total energy is still conserved. So it's fine. Interaction energy is becoming stored in some, for example, in chemical reactions. It's stored in some covalent forces and etc. etc. Right? Yes.
But the interaction between the particles happens not only in the boundary if particles can move between.
All right. Yeah. Great question. So if I allow those guys to move, okay, then it can change stuff. Let's assume that I'm not allowing. Or if I'm still allowing, I don't care about this interaction. So if those systems are exactly the same, and there are basically almost no interaction between the particles, I don't care if there is a boundary or not. Yes.
I also have a question. The interaction energy is an energy that is currently stored in the boundary.
In the boundary.
In the boundary between these two, and not energy that passes from E1 to E2.
No. They can exchange energy, but there is some specific energy inside
Let's
the wall.
take some of the price, please.
Yeah. Okay. Now, I assume now what I know now that any system I can define by its energy. I know that the energy is an extensive quantity, basically meaning when I have two systems, I connect them together, the total energy is just the sum, that's it. And I do know that I need to control this energy somehow, right? So how I control this energy? First of all, I can heat the system. Heat energy, right? So I can take my system, I have here water, I can light the fire or turn the gas on or whatever. Fire. Then there are going to be some gas fumes. Okay, and I'm getting an energy of something that is going to rotate over here. Okay, so I can turn the heat energy, okay, of the fire by heating the water and then creating some rotation, which is a mechanical energy, right? So in general, we usually, when thinking about energy, we're thinking about mechanical energy. But if you study thermodynamics, all of thermodynamics is based on how engines works, how I can take the energy of the fire, okay, or heat, basically, and somehow convert it into mechanical energy. Okay. So I know that in general, any energy or changes in the energy can be derived by the changes of the heat and plus some mechanical energy. Okay? That's it. So in general, I have those two ideas. The conservation of energy is going to tell me, well, when you have some sort of a changes inside the system, it can appear due to flow of heat from one system to another, or it can be applied due to performance of work of one system upon the other. This is all the changes that I'm considering. Now, heat, we have some sort of an intuition about that we can turn the heat off or on, right, by turning the fire. Mechanical energy is actually very nicely defined. So what is mechanical energy? Well, you have seen through the 2, 3, 4, 5 years, whenever you started learning physics, that this dW is usually some force, right, multiplied by some variable. Okay? So if I have a force that's acting in direction x, and I have a force that's acting in this direction, so the work is the amount of force multiplied by the extension or translation of my particle. Now, but I can apply different forces, and I can extend different things. So in general, we're writing this in the following fashion, but F here is not a direction, and dx here is not, the vector here is not a vector of direction of F, and dx here is not a vector of direction of the translation. Okay. So F is the applied force, applied forces, and dx are changes in the extensive variables. Okay, so let's see an example. Again? Extensive. So I will remind you what extensive means. Extensive quantity, right? If I can with energy. If I have system A, Okay, and I have system B. Okay, so I add those together. Extensive quantity is this E of A, and I have here E of B. So now I have a composite system, and I have now this property is EA plus B. Okay, so think about it. I have a rod. Okay, another example. I have a rod. Okay. The length of this rod is L1. Okay. I have another rod. The length of this rod is L2. I add them together, I connect them. Okay, so I have one long rod. What is the length of this one long rod? L1 plus L2. L1 plus L2. This means that the length is an extensive quantity. So any quantity that satisfies this equation, I take the property of object A, I take the property of object B, I connect both objects, and I measure this new property, and if it's a sum of two old properties, it's an extensive quantity. Okay? Is it clear?
Yes.
Yeah, okay.
Thank you.
Where were we? So let's see the examples of applied force and change in the extensive variables. So if I have a system, a piston, right, and I know that the pressure inside the system is P, and the volume of the system is V. Pressure, volume. Right. So I know that the mechanical work that was performed on this system, according to this, is some general force multiplied by general displacement. My general force here is P. My general displacement is I'm going to change the volume of this chamber, right, by moving the piston up and down. So the work applied on the system is P dV with a sign minus. Why the sign minus over here? When I compress the system, the energy goes up. So for this system, what is F? Is minus P. Okay. What is dx? Is dV. So my coordinate for translation is volume, and my general force is pressure. Yes?
You talked about expensive quantities, and so you talked about energy expensive quantity.
Yes.
Then it's expensive quantity.
Yes.
Mass.
Mass is also an extensive quantity.
What is not?
Temperature is not an extensive quantity. Pressure is not an extensive quantity. And I can continue. All right? How they are called? Intensive quantities. Okay? So we are going to make, and it's an excellent question, we're going to make an important distinction. We have extensive quantities, okay, which are usually our coordinates. The energy is also an extensive quantity, but the generalized forces over here, those guys are intensive.
So actually, dW is multiply of intensive quantity.
Because it has to be, according to this equation, dW has to be extensive, right? So if my coordinate is extensive, my generalized force has to be intensive. Okay? Yes.
אני קצת מתסבך אותי מבחינת יחידות.
Okay. So you have P.
Okay.
What are the units of P? So the question is, what are the units? What are the units of force, of work?
אני יודע להגיד ש-P זה כוח חלקי שטח.
Exactly. So what is volume? So here I have force divided by surface. Okay. What is volume is, so this is F or Newton divided by m squared. What is volume is m to the third. So m to the third divided by m to the second is Newton multiplied by meter.
זה משכנע אותי שזה אנרגיה, אבל אמרנו ש-P זה F. בגלל זה אני קצת מסתבך.
Generalized forces. The only thing that you need to know that this expression gives you an energy.
Okay.
Okay? So, and eventually you look at this, oh, I have some sort of a coordinate, and I have some sort of a force. Whatever stands in front of the coordinate is my generalized force. Okay?
אז זה לא כוח, זה כוח מוכלל.
Exactly. Generalized forces. Let's
זה מה שאני...
change this as the generalized forces.
תודה.
Okay? Now, another example. Yes.
The coordinate is extensive.
If the coordinate is always extensive, the generalized force is always intensive. Okay? So for example, I have a rod. Okay? So the tension of this rod is T. Okay? And the length of this rod is L. Okay? So I have dW is TdL. Right? So now my generalized force is D, and my coordinate is L. I'm sorry. Now, it's important that you notice that it's not always just measurement of X. My coordinate can be volume, it can be surface, it can be length, it can be the number of particles, the mass that you mentioned. It can be the number of particles. It's an extensive property. And whatever is standing over here is called as generalized force. It don't have to be a force like here. Pressure is not a force. Okay? Pressure is not a force, but I'm treating it as a generalized force. Now, since I can have many generalized forces that are applied to the system, f dx means f1 dx1 plus f2 dx2 plus f3 dx3, and the number of coordinates and the number of generalized forces is unlimited. Okay. Yes.
So generalized forces are intensive.
Generalized forces always intensive. Coordinates, generalized coordinates are always extensive.
Okay. And now sometimes just relate to things like pressure as the force.
The force, yes.
Okay.
So it's a little bit confusing because we were taught forces, they are a very specific form of force, and pressure is not a force. But in this thermodynamic spectacle, force is whatever stands in front of the coordinates.
אפשר שאלה נוספת בבקשה?
Yes, another question.
הקו מעל ה-D-level, תוכל להזכיר לי מה זה מסמל?
Oh, so I will tell you in a second.
אין בעיה, תודה.
So up to now, we have something that describes the mechanical work, right? So this guy over here is mechanical work. Okay, but in the original equation, what we had, d is dq plus dw. Okay, so this is mechanical work. This, the work that has been produced by flow of heat. What I mean by flow of heat, so if you remember the nice cartoon that I have over here, I can lit on a fire, right? It will heat up the water. There are fumes that are going up, vapor. Okay, the vapor going up and it rotates some rotor. Nice. So I'm producing work by transforming heat from the fire towards the water. Now here I cannot really tell you about the extensivity or intensivity of the heat. We will talk a little bit about it later. But one thing I do know. So, and this is your question about why do I have this small, it's not dW, but it's d with some line over it, some bar.
It depends on the road you pick.
Oh, so it is not a differential, right? So for any function, we have a very nice definition. What is d of g? So if g is a function, d of g, okay, is some sort of a differential of this function, and it depends only on the starting point and the end point. Okay? I know that some sort of heat was transferred inside the system, but it's not on the initial state of the heat and the internal and the final state of the heat. I cannot define Q as some sort of a function, and that the only thing that I care about is what has been at the beginning of the process with the heat and what was at the end of the process of the heat. This is why it's not a regular potential. Everything that is connected to heating and cooling, it's usually not a process that we can define. I only care about the initial state and the final state. The process itself, how I got from A to B, is very important. When you're dealing with differentials, I only care about my starting point and my final point. Why? Because if I'm integrating dg from point A to point D, it's simply g of B minus g of A. It's not working like this when we're heating something. Okay? And there are a lot of physical examples that it's not only how you heat, okay, from what temperature to what temperature, but also how you started and what was your initial state and what you have done in the middle. So this is why I cannot really treat this as a differential. And since this is not exactly a differential, this guy is also becoming not exactly differential as well. Okay, so this is this simple questions.
Yeah, I have.
Yes.
In this problem with the pressure and the volume,
Yes.
dV is differential.
Yes.
Not with the little line.
Yes, exactly. So here I can
Yeah.
erase it. Yes.
Thank you.
Unless I'm doing this fast. Okay, so I will complicate it. If I'm doing this slowly, this is a differential. But if I'll take this and push it extremely hard, the amount of work is not going to be defined by the change of the volume multiplied by the force, by the pressure. It's not.
But then this equation is wrong. It's
Sir.
not about the line.
It's about the line. So it's about how I'm performing this change of this extensive variable. Okay, this guy over here, if you remember from thermodynamics, you have quasi-static processes. We will define them a little bit in a couple of minutes. But if it's work and differential, it really depends on the process and how fast you perform the process. Okay? So it's indeed that pressure multiplied by the change of the volume is the energy. Okay? But it's also a full differential only if I'm doing slowly enough. If I'm not, there's a lot of turbulent motion that inside the chamber, and then all of this equation is not exactly true. Or, moreover, it's not reversible. Right? So if I push it a little bit, okay, I exerted some amount of work. Now I release it a little bit, comes back to the same situation as it was before. If I do it really fast and then release, it won't. Okay? Yes? Oh, intensive, it is, so the question is, extensive quantity, we know, we define it. Now I'm telling you, this is an intensive quantity. What is an intensive quantity? It does not depend on the size of the system. It's irrelevant. The size of the system for the pressure is completely irrelevant. Right? I can increase the system plus as much and still the pressure can be the same. Okay. So any intensive quantity, by definition, is a quantity that does not depend on size. Yes.
כאילו, אין
The
לי קשר
equation
בין שני
of
המושגים?
dw.
כאילו, אין קשר בין שני המושגים?
No, one is something that depends linearly on size. The other one is independent of size. Okay? Yes.
So the dw equals minus p dv. This is true only in quasi-static.
Yes. The answer is, as you studied in thermodynamics, this is a true differential only when you perform the process extremely slowly.
Yeah, with the TDS.
Yes. We will see it in a second. All right. Now, how we control the heat? So we know how to control the forces. Now the heat is we know that it's not a full differential, okay? And we know, well, we can lit a fire or whatever. But generally, if we want to control the heat, and I'm not going into how exactly we do this in an experiment, but in order to control the amount of the flow of heat, right? This is the important. I don't care how much heat I have inside, but I do care if it flows outside or it flows inside. I usually use the term adiabatic boundary conditions. What is adiabatic boundary condition? So if I have a system, adiabatic boundary conditions prevent the flow of the heat to the system and out of the system. Okay? So in order to control heat, I can put on adiabatic boundary conditions or take them off. Right? So this is my control parameter.
It's the control parameter of any intensive
Yes.
parameter, maybe.
It's well, I can. You're completely right. So I can have different boundary conditions that will control the pressure or they will control the tension. You're completely right. But usually we are going to talk only about adiabatic boundary conditions and say, well, everything else stays constant. Adiabatic boundary conditions? No heat flows outside of the system or to the system. Even if I lit a fire over here, the amount of heat is not going to penetrate to the system. Okay, so we know how to control this guy. We know how to control this guy. There are also other constituents that we're going to use in this class. So this is some sort of a crash course on thermodynamics. Is it too fast or is it too slow? It's okay. Okay. So up to now, we know is energy. Okay. What else do we know? We know that we have pressure. Okay. What else? We have volume. No, I haven't told you anything about entropy. I don't know what entropy yet. Okay. Pressure. Volume. We have heat. Okay. Q. Okay. Which we don't really understand what it is. We define it by some adiabatic boundary conditions, and our intuition about the heat is extremely loose, right? Because I know what force is and I know what the volume is, but how I exactly look on heat, right? Now we also going to use number of molecules. So Ni or N1, N2, N3, N4. So is number of molecules of type 1. Okay, and 2 is number of molecules of type 2. And 3 is number of molecules of type 3, etc., etc., etc. Now, are the number of molecules are extensive or intensive property?
Extensive.
Extensive. Okay, so if I'm looking on this guy, my mechanical work, okay, so I have a force multiplied by some sort of, some sort of coordinate, extensive quantity. So if I'm looking on dW, I'm writing here dN1 plus dN2 plus dN3. Okay? Let's assume that in my system I have 3 types of molecules. They are also called composite variables. חלקיקים מרכיבים. Composite variables. So let's assume H2O, right? I have H and I have O, so that I have 2 molecules, or 2 atoms, right? All right. So if I know that the change of the energy, the work, the mechanical work, is associated with the changes that I perform to my extensive variables. So if I'm changing the number of N1, the number of N2, the number of N3, I need to have generalized forces that are standing in front of dN1, right? How I call them? Here I'll call it mu1. Here I call it mu2. Here I call it mu3. And what is this mu? It has a name. Do you know what it is called? Chemical potential. Chemical potential. Mu. Right? Mu equals chemical potential. And in general, I can write dE equals to dQ minus P dV, right, plus mu dN, or sum of I ui dni. This is my first law of thermodynamics. The change of the energy is due to the some changes of the heat, okay, the flow of the heat, and mechanical work, which is pressure, volume, and some composite variables. Yes.
Could you please explain? What, how the mu1 or mu2 or mu3 creates a work or anything like that?
Okay. So I just define it like this.
So you just said that they do according to this thing.
Yeah.
And what is the?
So if this equation, look on this. If this equation is true, E depends on what? It depends on N. So if I want to define the chemical potential, I simply say dE to dNi equals mu I. This is my definition. So I'm introducing new particles inside the system. Okay? My extensive variable, which is the number of the particle, is growing. Okay? And I'm recording how my energy is changing, and the rate of the change of the energy is the chemical potential.
And it something depends on the material you have there.
Yes.
And what again is composite variables?
The different types of molecules that I have inside the system.
So that's a number of a specific type of molecules. That's
Yes. Yes.
לא יודע אם זה משהו שאל, אבל כשאנחנו עושים סכום על I על UI NI, אנחנו לא מדברים על כל מול בפני עצמו, אלא על סוגי המולים.
Yes. So the question is, when I have this sum over here, I'm summing over different types of moles of particles. Yes. Okay. Yes.
לא אמור להיות קו כזה קטן על ה-V וה-N?
Not exactly. So it's almost a potential, right? But again, I cannot say that this is like this. Why? But because the number of molecules, it's completely independent of how I introduce them. So the mu is going to be probably dependent on the process, but I have a specific number over here, and then I have specific number over there, and it's completely reversible.
מה לגבי ה-V?
Oh, so V.
כאילו פשוט מפריע לי שה-E אין עליו קו ועל ה-Q כן יש. וזה קצת...
So let's add it over here. Okay? because I'm assuming that my process is quasi-static, so I can control this and reverse it. I can control this guy. This guy in a couple of minutes I will throw away, okay, and introduce a new quantity, and everything is going to be the regular potential. Okay, yes?
The number of molecules is it's an integer, it's a whole number. How can you find an infinitesimal quantity?
Okay, so I can talk about, so you're completely right? So I have 1, 2, 3, 4, 5 particles, but I can talk instead of measure the number of particles, I can measure them not in numbers, but in moles, for example. Okay? And then my system is great. So it's never a change of one molecule or two molecules. It's huge changes. Okay? So usually these DNs are not 1, 2, 3, they are big. Okay, and I'm assuming that I change the number of moles, so I can somehow define those are infinitesimal changes. Okay, so think about if you do not like the number, think about the mole.
Yeah, so then it's like 1 over Avogadro.
Exactly, and it's huge.
So it's a number of moles.
As you like. As you like. So it depends on the literature. In some literature, they are simply saying the number of particles. In some of the literature, they're using the number of moles. It's not really, doesn't matter as long as you assume that the number of particles can be a continuous variable. Okay? Question?
Yes.
Yeah.
שאלה. איך נגיד לי שגם המשוואה הזאת עם המיו והעבודה נכונה וגם המשוואה עם האנרגיה נכונה?
So the question is, how this is true and this is true?
No.
This is true? Okay, because this is defined when I'm talking about transition between equilibrium states. Okay? Okay. Equilibrium states, and I will explain it to you in a minute. Okay. Okay. So this is in thermodynamics. In this first class, part of this class, we are going to operate with this equation. We're in a couple of minutes we'll kick this out, and our variables are usually volume and our composite variables. Okay, so now what is our question over here? What do we want and need to understand in thermodynamics? When you were studying thermodynamics, what are the important questions?
What are entropies?
No, we don't know about anything about entropy yet.
How much work can this engine deliver?
What is the stable
Exactly. So how much work can this engine deliver? Or how good this engine? Now, if I'm not talking in the language of the engines, okay? If I'm not talking in the language of the engines, so thermodynamics was developed as a science by engineers, okay? As a science that described how good engines can be. Okay? Very important question. Now, later on, physicists described all those original postulates about engines in some different language. Okay? So, the question about how good or how much work the engine can produce is translated to the following question. If I have system A and I have system B, okay, what will happen to the system if I will erase some internal constraint? Okay? So if I will take two systems and they are somehow separated, they can be separated by adiabatic boundary conditions, they can be separated by some rigid wall that does not allow penetrations from particles from A to B, etc., etc. And the basic question of thermodynamics is what happens to this system which is closed and usually have adiabatic boundary conditions around it. What happens when I erase some internal constraint or some internal variable is changed somehow? what will happen to the system. So it was system in some state A, system in some state B. I change something internally, not externally, internally. The system is going through some process. I come back, and I see now a composite system. Okay? They are mixed together somehow. And the question is thermodynamics, can I predict what is going to be the state of the system after all of this mixture? This is the basic question of thermodynamics. And don't ask me exactly how it's translated to questions about engines, but it can be translated. Now, I mentioned here in this question, so there is a starting state A of the system A, and there is some specific starting state of the system B. What I mean by starting state? So we all know that if we do something, okay, usually if I'm going to hold this marker in my hand, I'm standing still, this marker is not going to do anything. It's not going to change by a lot, right? And I'm assuming that it's in some specific state. Okay. Moreover, I do assume that if this state is not changing as a function of time and can be described by small number of extensive variables, I call this state an equilibrium state. So in Hebrew, מצב שיווי משקל. What is מצב שיווי משקל? What is an equilibrium state? I leave the system on its own, and the system is not going to change from now till eternity. Moreover, it can be described by small number of variables, extensive or intensive.
זה המצבים ההתחלתיים של A ו-B?
Yes. So when I'm asking my basic question of thermodynamics, I assume that A is an equilibrium, B is an equilibrium. I do something and I wait till a new equilibrium state occurs, and I ask myself, can I predict what is this new equilibrium state can be? Okay? So it is very important to understand that thermodynamics is trying to describe what happens in equilibrium. In the last 15, 20 years or so, there has been a lot of development of what is called non-equilibrium thermodynamics. We are not going to talk about it. We are only talking about equilibrium states. Okay? So again, it's very important. Equilibrium state defined by small number of variables. What variables? Extensive or intensive. We will see why it can be a mixture of both. And it's not changing as a function of time. Now, most of the system that we look on, we say, well, they're quite in equilibrium. This marker is in equilibrium with its environment. But there are also some peculiar systems which are not changing as a function of time, but they are not in equilibrium. So this glass, for example, is not in equilibrium. We don't see its changes. Nothing happens to this glass. Okay? It can be defined by temperature, by the pressure of the outside. Okay, but it's not an equilibrium. So there are systems that seem that they are not changing, that they are not in equilibrium. Usually they are called glassy states. It's a very peculiar nature. For us, we are not going to treat glasses, we're not going to treat equilibrium and non-equilibrium system. Only systems that are not changing as a function of time, described by a small number of variables. For us, it's equilibrium, and those are the states of interest. We start from equilibrium, and we end at equilibrium. Yes? We assume, okay, so the question is, why I assume that I need a small number of variables?
זה הגיוני, אבל אני שואל כאילו, כי זה בעצם אומר שזה כאילו מצב על הסתברות הכי גבוהה שיש איזשהו תיק כזה.
Okay, So the question is why it sounds reasonable that small number of variables, but why do it has to be as a small number and not a large number? So you remember the starting point of my talk that I have one mass and I add another one and etc. And the forces are important. So what we learned from experiments that somehow for most of the system that we look, not the glasses, but most of the system, 99% of the system, you can define small number of extensive or intensive variables, and that's enough. You don't care about the internal interaction, you don't care about a lot of different things, or the specific structural state, or how many blue particles are over here, and how many red particles are over there. You don't care about any of that. You only care about pressure, the composite numbers, and that's it, for example. And that's enough. That's enough to define this equilibrium. Okay? You are right that huge systems have huge number of ingredients, and it can be very important where exactly all those different ingredients are. We have an Avogadro number of particles, right? It's very important where this particle is and that particle is, but for the equilibrium state, you don't care.
אז שאמרתי לפני כן שכאילו אפשר לתאר את זה במספרים גדולים, זה רק כאילו שיעור משקל?
Yes. So the question is, when I'm talking about global laws and description of big systems is only in the equilibrium state? So the old question was yes, and the new question of the last 15-20 years is maybe. Okay. So we do know that there are some systems that are out of equilibrium, but we can still use this framework of small number of variables to describe them. It's always about how specific I should be, right? So if you're a chemist, you have to be, or a medical doctor, you have to be very, very, very specific. Physics is about general laws, very simple, okay? And this is the assumption over here. I need a simple law with small number of variables to describe something. If I need to describe all the different positions of the Avogadro number of particles, I'm lost. I cannot do anything. But if the only thing that I can tell you, well, how many particles are inside, what is the volume, what is the pressure, it's enough, and that's great.
רגע, ומה אם בכל זאת, כאילו, נגיד אתה נמצא במשהו שהוא כאוטי, תורת ההפרעות, כאילו...
Later on, okay? Yes. Yeah.
Why is glass not equilibrium?
Why is glass not? So if you will measure the width at the bottom of this glass of the window now, and you will measure it in 30 years from now, you will see it's going to change. Slowly. The process of glasses, you don't see them on a regular daily scale, but when you're talking about centuries, you see that this actually is a flowing matter. Flows. There are experiments with glasses that are done for 40 years, and they see that it can become some sort of a droplet that drops, and another comes and another comes.
So all the lamps that are from glass.
Yeah, but you will throw them into the garbage, in half a year and a year from now. Nothing.
Glasses lamps that are in museums.
It depends on the specific of the glass. The amount of time that it has to take for the process to come by. Other questions?
I have one.
Yes.
כשמדברים על equilibrium state, אכפת לי רק מגדלים מקרוסקופיים שיתארו את המערכת, כי אמרת שכשאני באקוויליבריום לא משנה לי איפה נמצאים כל החלקיקים, אלא מעניין אותי רק תכונות של כל המערכת.
Exactly. Excellent question. So the question is, when I'm talking about the equilibrium state, do I care about the microscopical structure, the macroscopical properties, or only about macroscopical properties? Now, thermodynamics is a science that started in the 19th century. They had no idea that there are atoms and what atoms are. Okay? So the only thing that they cared about and what we're going to care about in thermodynamics, not in statistical mechanics, but in thermodynamics, are only macroscopical properties. Okay? All right. So, great. This was the first law of thermodynamics. Now we're coming to the second law of thermodynamics. And the second law of thermodynamics is focused on those equilibrium states.
Is that the third law, equilibrium state?
Sorry?
Is the second law entropy increasing with third law equilibrium?
Yes, so the second law is connected to the equilibrium states only.
Generally, all laws are basically just, all three are basically just one law when you realize.
There are definitions of those three laws in one sentence, yes, but you cannot understand this. Or I, to that matter. Okay, so the second law of thermodynamics. Okay, so let's lay it from people. There is a function S E of x that is defined for equilibrium state. And depends only on the state. Okay, what I mean by depends only on the state, that it depends only on E and the specific values of E or specific values of the extensive quantities. Okay. This function is extensive and monotonically grows with energy. Okay. S E x equals entropy. Okay, so this is a very bad definition. Why? I don't know how to tell you what exactly the energy is, right? I haven't defined you. I used examples to tell you what energy is, right? And then I tell you, well, you don't understand what energy is, but there is such a thing as energy, and it can be this or that or that. There is not a general definition. The only definition that it's conserved. And then I invent another crazy theory. I'm saying, well, there is another function, and it's a function of energy, and I cannot tell you what it is. I will call it entropy, and I know that it depends on the equilibrium state, and I know that it grows with energy. Okay? That's it. That's the definition, and this is the second law. So there is a slight continuation. If a state D can be reached adiabatically from state A, then SP larger than S. Okay. So what it means is that I have a system, okay, and I close it by adiabatic boundary conditions. Right, and the system starts, I let it go, okay, I change, for example, some internal constraint, okay, so I had one equilibrium state, and I'm changing it, and it's going to flow to another equilibrium state, so it's starting from A, it's going to B. I know that my entropy is going to grow. Okay? Any process that is reached adiabatically, any state B that is reached adiabatically from state A, I can define for both states the entropy, and I know that the entropy is growing. Okay, so here, the entropy is growing as a function of energy, Here it's a different postulate, a little bit different. It says, oh, I don't really care about the energy, right? I know that the entropy itself is growing. Yes?
יכול להיות שהמעבר מ-B ל-A הוא כזה שבעצם אנחנו מאבדים אנרגיה?
Maybe.
לא, אני פשוט מסתכל על ההשוואה בין השתיים, אני אומר...
You don't care. The only thing, so the question is, can E change, decrease or increase? I don't really care. Okay, so this postulate says, as long as the transition is adiabatic, okay, as B is larger than SA, I less care about what happens with the energy. I know when the energy is growing, okay, then S is growing. Okay, so you're saying, well, if I will create some sort of a process when the energy is decreasing, okay, when the energy is decreasing, then S has to decrease. But I haven't told you anything here what happened to the other part of the system.
אז מה אנחנו רואים פה בעצם?
That as long as then that usually in a closed system which is reaching from state B to state A, adiabatically the energy can grow. But all of this and that usually are, we are treating the situations when the energy is constant. Any other questions? Right? כן.
מה הקשר לתהליך הדיאבטי פה? כאילו, אנחנו למדנו בטרמה שהחוק השני לא קשור לתהליך הדיאבטי.
Okay, so there are many definitions, but I'm sure that the definition that you had in thermodynamics can be achieved starting from this definition. The definitions of thermodynamics, so the second thermodynamic law, there are many of them. Okay? So, but they are all equivalent in some sense.
We learned that this happens in a closed area.
So this is usually, we teach it about adiabatic. The closed is...
למה זה אומר את אותו דבר? שינוי הדיאבטי זה שינוי שפילו מתבצע לאט לאט?
No. Adiabatic English. Okay, so the claims are, has it to be a closed system? Claim number 1. Claim number 2, why it has to be adiabatic? Adiabatic is very slow. So to answer your request, adiabatic is not about slowness, it's about not getting any heat out from the outside or getting losing out heat to the outside. Okay? So this is adiabatic. About the closed system, and this is related to your question, can the energy of the system increase or decrease during the process? So usually when I'm talking about B or I'm talking about A, and if this state is equilibrium, if I'm letting the system to be open, okay, this already not going to be an equilibrium state. Okay, so when I'm telling you that I'm reaching an equilibrium state B, and I started from an equilibrium state A, I do assume that the process haven't changed any particles, any heat, any energy with the outside. Otherwise, the two states are defined by different parameters. Okay? So the change from A to B is achieved only by modifying some internal parameters and not external parameters. Right? And if I'm not modifying external parameters, remember this the equilibrium state is defined by my macroscopic external parameters. And if I'm not modifying them, then this is the same equilibrium state. Okay? So again, I'm reaching B starting from A when I'm not modifying my external parameters. I'm modifying my internal parameters.
לא רק בשורה התחתונה, זה צריך להיות כאילו, זה יהיה כאילו לרוב כאילו closed?
So for your purposes, it's going to be closed. Yes. Yes. All right. No, I want to be a little bit more general because you will remember closed, and I want you to focus on equilibrium, and it's a little bit different. Okay. So how different are small peculiarities, but I want to operate in the sense that I'm treating only equilibrium systems, not only closed but equilibrium.
אז יכול להיות דוגמה למשהו שהוא לא closed והוא יהיה כאילו...
There are when we will talk about ensembles in statistical mechanics, you will see closed system and equilibrium system, and the distinction will be clear. Okay. All right, so we can define S. We know this property. Now, if you remember, we have this peculiar behavior of dE, right? We have heat over here, and heat is never a differential, and I cannot basically operate mathematically with quantities which are not differential, and specifically functions that I cannot define properly, and the heat is a function that I cannot define properly. Okay. So my goal now in the next 5 minutes is to start from this dE, which I don't know if I have a bar, I don't have a bar over here, and dq minus pdv plus sum on I, mu I, d and I, and to reach something which I can use later, right? Some sort of a proper mathematical description of the energy, where I'm going to use the entropy. Okay? Right now, I don't know what this is, and this is a problem for me. Okay. So let's start. So I know that S is a function of E and X. Right? It's a function of the state only, of the equilibrium state that's defined by the energy and the extensive properties. What is ds? So we know it's a function, it's a mathematical creature. We can write a differential. We can do this, ds to dE, d plus ds to dx dot dx, right, when E is constant. So what is the sign? This is a partial derivative of S with respect to E when I'm keeping all the quantities, my extensive variables, constant. Okay, so what is this guy? It's simply ds dx1 E dx1 plus ds dx2 E dx2 plus ds dx3 dx3, etc. Okay. So this is my ds. Now, I can write this dE, I can take this dE over here, right, and introduce all of this stuff inside. Okay, so ds equals to ds to dE x multiplied by dq plus ds to dx E plus ds to dE x f dot dx. Okay. Now, for simplicity, in a second, dn equals 0. Okay. We don't really care about this dn over here. What I've written over here, where? I have dE. What is f dx? So all of this, I don't need it. So all of this, f dot dx. Okay? Right, so we have this, we have this, we have this. Very nice. Now, where? F dx. And you have ds to dE. just substitute all of this over here. Okay, so you have ds to dx multiplied by dx, and you have f multiplied by ds to de multiplied by dx. Right? Now, let's assume that ds equals 0 and dq equals 0. Okay, so I'm started from A, I went to B, two equilibrium states, but those states are produced by an adiabatic transition, so dq equals 0, okay, adiabatic transition. And I assume that I can reach from A to B, okay, or I can reach from B to A. Okay, so those two states are connected in such a way that I can start from A and reach B by changing some internal parameters, or I can start from B and change and go to A by getting back the same external parameters. So this is a reversible process.
It has to be quasi-static, right?
Usually, reversible process. Okay. So remember, if I can start from A and reach B in adiabatic fashion, then SD larger than SA. But if I can start with B and reach A in adiabatic fashion, then SA larger than SB, which SB equals SA. Okay? So in any reversible process, the change of the entropy equals 0. The process is adiabatic, so I have dq equals 0.
איך זה מסתדר במשוואה? או שאנחנו עכשיו מלבישים את זה?
Now we introduce this, and we say this is 0, this is 0, so we have ds to dx plus of e plus ds to de x f equals 0. So this is the equation that we got. Now you can tell me, Stas, great equation, but the problem is you looked on two specific equilibrium states, A and B, and you look on a specific process which is reversible, which is quasi-static or whatever. It's not really physical, right? You change something very, very slowly. Most of the processes are irreversible. And you have assumed that dq equals 0. Okay, so this is a very specific but not general equation. And here I can tell you, well, you're wrong. Why? Because S is a function of state only, right? It's not a function of the process, how I got to the state, is a function of state. So if S satisfies this, okay, it satisfies no matter how I reach the state. Okay? So the way how I got this equation is completely irrelevant because S is completely defined by the specific position. It's defined by the specific values of E, specific values of V, specific values of N. I don't really care how I got myself into this situation, okay? And only the outcome is what matters. So this equation is general, all right?
Can you repeat this? Why general?
Because if it's satisfied for one specific process, it is going to be satisfied for any processes because S is a function of state and not a function of a process.
So if I create another equation from another process, it will be general?
Yes, because S is only a function of the state. Okay.
So that's because it has the same parameters from the beginning and the end?
Yes. It doesn't matter how you got, these quantities are local. The derivatives are local, right? So it doesn't really matter how I got into the position, it's only matter where I'm standing right now.
As long as I keep the entropy the same, I should...
Yes.
Can you explain how you got the equation where you took the first law and introduced it to the second law?
I already erased it, but I'll repeat it in a minute. Let me come to my conclusion. 1 second, okay? Okay, so we are almost there. We're almost there. Now, additional thing that I want to tell you is that I know the ds to dE. Okay. I know that this guy is greater than 0, right? So the entropy is a monotonic function. I know that. This is how I define it. Now, it basically also tells me that dE to ds is greater than 0. Okay, so S monotonic function, monotonic growing function of E is a monotonic growing function of S. This guy I call temperature. Okay. So temperature for me is the derivative of the energy with respect to entropy. Okay, now we can go into this equation over here, where we have ds to dx equals minus f divided by t. Why do I need this guy? I know that ds equals to ds to dE plus ds to dx of E dx. Okay. So ds to dE is equals 1 over temperature. dE. Where? X. Yes. Okay, dE plus minus F divided by T dx. Okay. Let's multiply both parts by T, and I'm getting T ds equals dE minus F dot dx, or dE, which is now a full potential, right, equals to TdS plus F dot dx. Okay. And this equation you used many times, hopefully, in the class on thermodynamics, and we also will see how to use it. Okay. But now it's already a mathematical equation, right? Not some stories about heat that I cannot define. I have a function, entropy, we'll discuss it. I have forces, generalized forces. I have general coordinate. I have regular differentials. And now I can apply the full force of analytic functions or analysis, mathematical analysis, to treat the different systems in thermodynamics. I want to know what will happen to the energy. I need to know, operate with entropy and my generalized coordinates. So I can make predictions, I can make evaluations. This equation I can deal with. Previous one, the conservation of energy, is a little bit useless. Okay? So in Tuesday we will see how we treat this equation and how we deal with it. Thank you.
So long.
Okay, bye. Of this state. Only, depends on this אנחנו יצרנו מספיק, יש לך איזה שהוא התשובה הייתה נכונה. כן, בדיוק. כל המטרה הייתה, מתאים לי לסיים בגילים, איזשהו מסלול, לא משנה. העיקר שיש לך מסלול ואתה יודע ליצור איזשהו משוואה. ברגע שיצרת אותה, המשוואה היא לוקאלית. והיא תלויה רק בפרמטרים, או ב-B או ב-A. וזהו, בסוף נכון, בדיוק. המקרוסקופי. כן.
לא, אבל למה לשמוע לך אני מצננת?
פשוט ספציפית עבור המדריך של הלחץ לא ממש, כי באיזשהו שלב אנחנו אומרים בוא נטפל רק במקרה של פחות
זה מה שבינה אמרה, שהדינמיקה רק
זה נכון, זה נכון. אתה מתחיל נניח במצב א' ואתה עובר למצב ב', עכשיו אתה כמובן יותר לאט, אבל המשחק הזה רשמתי אותה, היא נכונה עבור המצב. אני רוצה לדבר על מצב, לא איך אני עובר ממצב א' באיזה דרך למצב ב'. אני אם אני נמצא במצב ובסביבה מאוד קצרה של המצב, זה בסדר. כשאני עושה שינויים גדולים, הקשר הזה מתחיל להישבר, ואז רק קוואזיסטטי.
ואז רק זהו.
נכון, נכון. כלומר, ברגע שהשינויים שלך גדולים מדי, אתה לא יכול להגיד שאתה נמצא בסביבה. זה שינוי מאוד קטן שם.
כן, זה ממש בפרק זמן מאוד כאילו קצר.
אז כל עוד אני נמצא בסביבה המאוד קרובה של הנקודה, זה תמיד נכון. כשאני רוצה לזוז רחוק מהסביבה של הנקודה, אז זה כבר לא כן, נכון.
אתה צריך כאילו את המסלול, אתה פונקציה של המסלול.
בדיוק, אני צריך ממש להיות ספציפי לגבי המסלול. כן. אבל אל תדאג, אנחנו בעיקר נתעסק עם מצבים, ונגדיר את המצבים עצמם, לא את השינויים המאוד גלובליים שיש.
כן, כי היא אמרה שכאילו, משהו שלא קוואזיסטטי, אז זה מאוד...
זה מסובך, לא, כי אתה צריך לתאר לי בדיוק את המסלול. ממש נניח, איך חיממת, מאיזה נקודה התחלת ומה עשית באמצע, ולא טמפרטורה התחלתית, זה טמפרטורה סופית.
כן, כן.
לא ממש, לא,
הוא גם טוב. אני לא גם פה, אני יודע שדנה יש את נוער, מאיר גילה דעה אמור להיות
זהו, כל השאלות שלכם
אנחנו, רגע,
שאני לא תרגמתי בעצמי.
ההגדרה שאני מתחיל במצב A ואני עובר למצב B, הדיאבטי ספציפית, האנטרופיה של זה תשים לב,
כדאי להגיד את זה.
אני יכול להגיד, זה קורה כשאין לך תחשוב פה איזה קשר יצרנו.
כמה תיכוניסטים, זה שאלה.
אנחנו אמרנו שמה שכל זה בעצם שווה ל-DQ.
מה המודל? יכול לראות.
אז אתה יכול להגיד לי רגע, אתה מחמם, האנטרופיה שלך עולה, זה נכון. אבל זה איזשהו פועל יוצא כזה של מה קורה אחר כך. כשאתה רוצה להגדיר את זה, זה פחות אכפת לך מעבר לזה, אבל זה אומר משהו קצת יותר חשוב. גם שזה שווה לאפס. זה עדיין יכול להגיד. זה הכרח.
בהכרח בדיאבטי הוא עולה.
נכון. אז אתה לא מתחיל מזה ואתה לא יודע מה לעשות עם הדיאבטי, אתה אומר אני מתחיל מהדיאבטי, ומתוך זה אני אקבל גם את מה שאתה טוען עכשיו.
אני כאילו מתחיל מהתנאי הכי חזק, מה שבדיאבטי זה עולה אז בטח שבלא בזה.
בדיוק, בדיוק, גם נקודה רבה. בבקשה.
אני יכול להיות שזה מה שהוא שאל, אבל אני לא ממש... אני הגעתי למסקנה הזאת ספציפית, אתה... באתי והוא הפיך, ואז
ואז אמרת,
אני הגעתי למצב, כן, אני אמרתי, זה טריק שתמיד מבלבל את כולם וגם אותי, אז אל תדאגי. אני הגעתי למצב הזה ברגע שעל ידי זה שאני הכנסתי את שתי הנחות האלה. כלומר, הנוסחה הזאת הגעתי פשוט על ידי הצבא. אחרי שהגעתי לנוסחה הזאת אמרתי, אני אמחק את זה, ובואו נמחק את כל זה. ואז אני נשאר רק משהו כפול dx שווה ל-0. dx זה שינוי כלשהו, ולכן הוא שרירותי. לכן כדי שכל זה יהיה שווה ל-0, כל זה יהיה שווה ל-0, מה שבסוגריים חייב להיות שווה ל-0. אוקיי? שזה זה. עכשיו, תחת אילו הנחות, ש-ds שווה ל-0 ו-dq שווה ל-0. אוקיי? יפה מאוד, עד פה מתמטיקה, הצבא מקבלים. עכשיו פה אני עושה את הקפיצה המחשבתית שלי. אני אומר, אם זאת משוואה שנכונה עבור זה שהפעלתי תהליך מאוד ספציפי, היא נכונה תמיד. למה? כי S היא פונקציה של מצב. לא אכפת לי איך הגעתי למצב, אכפת לי שאני נמצא בתוך המצב. תחשבי על זה ככה. זה כשאני אומר, אני נמצא בריבוע הזה. אוקיי? אני נמצא בריבוע הזה. וכל מה שמגדיר אותי זה המיקום שלי בריבוע הזה. לא אכפת לי איך הגעתי לריבוע, האם קפצתי לתוכו, לא קפצתי לתוכו. ברגע שאני נמצא בריבוע, אז אני מוגדר כמשהו בתוך ריבוע. אז אם אני הצלחתי למצוא את הנוסחה הזאת, שהיא נכונה, והיא נכונה בכל מצב ומצב, בכל מצב ומצב, המשוואה הזאת נכונה. למה? כי אני יכול, ניקח מצב B, אוקיי? ניקח מצב A, נעביר מ-A ל-B, בכל הדרך שסיפרתי לך עליו, לפני זה, ואני נמצא עכשיו במצב B. במצב B הנוסחה הזאת נכונה. בגלל שאני מוגדר לא על ידי איך הגעתי ל-B, אלא זה שאני נמצא ב-B, זה נכון לכל מצב B.
איזה, זה כמו שלמדנו כאילו בנותחום זה טרמו, זה אותו דבר. זה פשוט משוואת מצב, זה לא משוואת כאילו תהליך.
נכון. בסוף, יש לי, אז זה תלוי בפונקציה שאתה מסתכל עליה. חום הוא לא משוואת מצב. אנטרופיה, אנחנו אמרנו, היא משוואה שמוגדרת על ידי E ו-X. תקבילי את E, תקבילי את X, אוקיי? והאנטרופיה מוגדרת. עכשיו, מתמטית, מה שזה אומר, זה נגזרות מקומיות, אוקיי? זה כל מה שזה מוגדר על ידי המצב עצמו. הנגזרת של S לפי X, הנגזרת של S לפי E, זה מוגדר על ידי המצב. אבל לא אכפת לי איך הגעתי למצב הזה. זה הכל. הגעתי למצב הזה, באיזושהי דרך אני תמיד יכול להגיד, אני הגעתי באיזשהו תהליך רוורסיבילי וקוואזי סטטי וזה שלו והדיאבטי וכן הלאה וכן הלאה, הגעתי איכשהו למצב הזה. אם הגעתי לתהליך שתיארתי לך אותו ככה, המשוואה הזאת נכונה? תגידי לי כן, נכונה, כי אתה יכול להכניס את שני הדברים האלה. ואז אני אומר, אבל זה עכשיו לא אכפת לי איך הגענו. S לא מוגדר על ידי מה שהייתי לפני זה, S מוגדר במה שאני עכשיו. אנחנו תמיד חושבים, רגע, הוכחתי את זה בדרך א', ואז אני עושה פליק פלק באוויר ואומר לך, זה תמיד נכון. אבל זה כן תמיד נכון בגלל ש-S היא פונקציה של מצב. כי לא אכפת איך הגעתי למצב הזה, זה מה שנקרא תהליכי חסרי זיכרון. לא אכפת לי איך הגעתי לפה, ברגע שאני נמצא כאן, והצלחתי למצוא איזושהי נוסחה, היא תהיה נכונה תמיד.
עכשיו גם להדליק גם תכלס את S עם המספר מצבים, לא? משהו כזה.
אנחנו נגיע, כשאנחנו נדבר על מכניקה סטטיסטית. זה עדיין חזרה על טרמו.
לא, אז כמה זמן זה יהיה כאילו בחזרה?
זה תלוי בכם, היום הייתי קצת איתי.
היית איתי?
זהו,
אני רציתי...
יש לי חבר משנה שעברה וזה כאילו לא באמת...
כן, כן, אני מספר לכם את זה בצורה מודרנית ולא בצורה ישנה.
לא, מה זה ישנה? שנה שעברה, שנה שעברה. השתנית? משנה שעברה היה עתיק לשנה מודרנית?
רגע, אני?
כן.
לא, שנה שעברה, אני אגיד לך, לפני שנתיים, כן, הייתה קבוצה של סטודנטים שצעקו לא צריך חזרה על טרמו, אנחנו יודעים הכל, סטאס, אתה מבזבז את הזמן, מבזבז את הזמן. אז סבבה, שנה אחר כך עשיתי את זה בלי חזרה על טרמו. ואז היו צעקות, אנחנו לא מבינים, ולמה, אז החלטתי השנה אני עושה חזרה.
יש פה אנשים שעשו את הקורס לפני שנתיים.
נכון, זה העניין. לא, אנחנו נתכנס, כן, אל תדאגי. אנחנו נתכנס, אולי אנחנו נחסיר איזשהו, אני לא אספיק את הכל, כן? כי זה בעצם 4.5, זה בסדר.
אבל תאמליץ לחזור בכל מקרה לטרמו, כאילו על המחברות ולעשות.
לא, אני חושב שפה יהיה מספיק. כל מה שאני אספר לכם זה יהיה מספיק, אתה תיזכר בדרך.
לא, אנחנו לא רוצים ללמוד עלינו, אנחנו רוצים מכניקה סטטיסטית.
אף אחד לא אוהב תרמו.
דינה אוהבת תרמו.
מה? דינה לא מתעסקת בתרמו, אז אני חייב ללמד את זה, כן, אבל ברגע שאנחנו נתחיל לשאול אותה על מנועים, היא תברח, כמו כל פיזיקאי רגיל. כי יש סטודנטים סינים, סליחה רגע. יש סטודנטים סינים, כן, היו מאחורה.
הייתי מגיעה, אבל לא ראיתי את
לא ראיתי,
למה זה באנגלית כאילו?
כן.
לא.
זהו, כי סבנתי שאין לך מבטא בעברית בכלל. כאילו, דווקא יש לך מבטא באנגלית ואין לך מבטא בעברית.
זה מאוד מוזר. טוב, אבל המבטא הוא מוגדר על ידי הגייה של מספר קטן מאוד של אותיות.
נכון.
אז אצלי, לא נולדתי בארץ, אבל בערך בגיל 14 זה עשה מין שינוי כזה וכבר לא היה מבטא. זה הגייה של למד, רייש ועוד כמה. זה ממש הגייה של מספר אותיות ואתה כבר לא תזהה.
לא נראה לי יותר מבחן.
אז אתה יכול אולי לנסות גם כאילו אז רק שאתה מגדיר מושגים להביא אותם גם בעברית? פשוט לפעמים הרבה פעמים, אם רק תגדיר את המושגים אני אדע תמיד להיזכר.
אני אשתדל, לא שתשאל אותי. אין שום בעיה, אתה ראית, אתה שואל, אני מתרגם ומנסה לראות. אבל אני אשתדל גם להגיד לי.
לא, גם כולם פה מדברים באנגלית, לא נעים כאילו, כולם פה גם שואלים באנגלית כאילו, אני קורא
לאט, רגע, אתה יודע אנגלית? אתה מבין אותי?
כן.
יפה. אז זה רק עניין של קושי של להתחיל לדבר, נכון?
לא, כן, אבל...
תתחיל לשאול.
לא, אבל יש גם מילים שגם עצמם כן לפעמים לא כזה...
אני מפריע לך פה?
לא, זה שלך גם שאלה תוך כדי.
אוקיי, בסדר.
צריך לשאול למה שלא מובן.
כן.
אבל לפעמים אני יכול לשאול שאלה באנגלית, ואז אתה תחשוב שאלה אחרת אולי, כי אני לא אגיד ברור. אז שזה גם...
אז אני אנסה להבין, אז תשאל אותי כמו בעברית. אז תשאל אותי עוד פעם, סטס זה לא מה שאני התכוונתי, ואם אתה לא מצליח להבהיר את עצמך באנגלית, זה תשאל בעברית. המחלקה קבעה שזה יהיה באנגלית. כשבשנים קודמות זה היה, לימדתי את זה פשוט פעמיים במקביל, קורס אחד בעברית, קורס אחד קטן לסינים באנגלית, ואז הוחלט שעדיף שזה הכל יהיה מרוכז, וזה טוב לכם לשמוע באנגלית.
זה גם בגלל שיש קטע כזה שמאיזה שנה צריך, גם מי שיש לו כאילו פטור מאנגלית, אז הוא צריך לעשות 2 קורסים מהתואר שלו באנגלית.
אני לא יודע, אבל יש איזושהי...
בגלל זה עשו נגיד מצב מוצק ואותך באנגלית.
אני אגיד לך מאיפה זה התחיל. זה התחיל מסטודנטים בינלאומיים, שבהתחלה זה נפתח כל קורס, זה מכניקה סטטיסטית, קוונטים ומצב מוצק, נפתחו כל הקורסים פעמיים, אחד באנגלית ואחד בעברית, ואחרי כמה שנים הוחלט שזה יהיה הכל ביחד. ואז היה פולמוס מאוד גדול באוניברסיטה, איך זה שאנחנו מלמדים באנגלית ולא בעברית, ובסוף זה באנגלית.
לא.
כדאי לצפות על הרצאות עליי בעברית לפני שאני מגיע להרצאה הזאת?
זה לשיקולך. והסדר השנה כמו שנה אמרה כבר קצת שונה, נכון?
מה, לא, רק עכשיו, זהו, אחרי זה אנחנו מתכנסים.
ייקח עוד קצת זמן. אנחנו נתכנס, אל תדאגי. שאלה מתי.
יש רגע כמה דברים, אז זה היה מוקלט נכון כי הגעתי לכמה דקות איחור, ודווקא שמעתי...
אני חושב שכן, זה אמור להיות מוקלט.
הדקות הראשונות זה מייל.
לא, אולי יש כל מיני מנהלות כזה שחשוב...
בסדר, המנהלות זה מה שלא יהיה לך בעיה להשתים.
כן. טוב, תודה. ביי.
כן, רצית לשאול מה.
כן, משהו ממש קצר.
אם אתה רוצה לראות, בוא תשאל אותי בדרך?
כן. רק לגבי השאלה, אם השווית את כל זה ל-0, אז גם כל הדברים האחרים, יוצא פה ש-DS שווה כאילו...
זה מה שנותר.
כל מה שנותר הוא גם 0.
כן, כי אז היה לך DS והיה לך DQ.
DS פחות דו-S לדו-E כפול DQ.
כן, תסתכל, זה מה שהיה פה.
אז זה כאילו, זה משוואה עם חשיבות?
DS, לא, זה לא אכפת לך בכלל, ויש לך פה משהו, כפול DQ.
יפה. אז עכשיו אתה אומר שזה 0 באופן
כללי. לא, זה שווה ל-0, זה שווה ספציפית, אז אמרתי, זה תמיד שווה ל-0. ואז יש לך DS שווה למשהו, כפול DQ. עכשיו, מה זה המשהו הזה?
דו-S לדו-E.
יפה, זה T.
יפה, אז באופן כללי גם הדבר הזה הוא בעצם שווה ל-0.
כן,
דו-S שווה מינוס T DQ.
DS מינוס T DQ.
כן.
DQ. או אחד חלקי? כן, שווה ל-0.
בסדר. אוקיי, אז זה גם משוואה חשובה.
ובסוף מקבלים את זה, זה מה שאתה רוצה להשתמש בו. בזה עובדים עם
כן, עכשיו כן, משהו שאפשר בדרך. תמיד... למה אפשר להגדיר אנרגיה
האור כבוי, לא? זה לא כבוי. לא, האור לא כבוי.
איך אני מקבל אותו כאן? זה במשפט עבודה אנרגיה. כן. זה בעצם עבודה. איך הגדרתי?
ככה, בסדר.
ככה עובד? לא, בסדר, אם ככה. יופי, חיים. זה לנעול.
לא יודע למה לנעלים את העולם עצמו.
לנעול את ה...